Okay, hi everyone, I'm Amanda, and I'm going to talk to you about what we've been doing in the Polonius working group for the last 6 years. I've not been actively in the group for all those 6 years, but I've been on and off again in it. So the working group consists of, right now, the people doing work is me, Nico Matsakis, and Remy. And then there have been a bunch of other people who have done stuff and then moved in and out of the group, basically. So I think any talk at a Rust conference should start by describing why Rust is so cool, because you're the choir and I'm preaching to you right now. And I mean, it has a lot of cool things, like you can write an OS kernel. It's rather painful, but you can do it. And you've got a bunch of other stuff. But I come from the academic side, and the thing I really focus on is the fact that I get to use cool, advanced research type systems in a real-world environment where people actually use them to write real-world programs, which means that, of course, you can also do secondary studies on how they use the research type systems. That wouldn't be possible if you made a toy language. So that's really what it brings for me as a research-oriented person. And the research type system in question is primarily ownership types. Sometimes they're associated with linear types. Let's not go into the details of what that actually means, because that's an entire separate talk. But essentially what we mean when we talk about ownership types is that every value has exactly one owner, and that also means that when a value gets out of scope, you can deallocate it. That's roughly what you mean by ownership types. And usually this is paired with borrowing, because if you just have ownership types, it's a pain to work with. Borrowing is what everyone in other languages calls references, but it's essentially when you have aliases to something that you don't have. And of course, like the rules of borrowing are the familiar ones, that you can only have one mutable reference to something, and the reference must be valid for the duration of your use through that reference. So you must statically guarantee that you cannot have any weird shenanigans going on. And this is essentially what gives you data race freedom, and it gives you freedom from memory problems that you would see in other low-level languages. This is really the secret sauce to Rust. And most of you know this, or all of you know this probably. And a language like Rust that's, well, imperative-ish, you get safe and easy memory management, because you can basically do allocation and deallocation without having to think about it automatically in the compiler. But it turns out that this is the holy grail of every language, because another problem that you might have is if you're doing object-oriented language design, you want to be sure that your objects don't escape from inside of other objects. So you might have internal stuff. And this also gives you that. And it also gives you, so if you have a functional programming language, generally those are dog slow unless you cheat and under the hood change them. And the way you cheat is by ensuring that you have the sole copy of a data structure and then you do in-place updates. So this really is a holy grail. It does everything for everyone. And the thing in Rust that does this is the borrow checker, which you've been arguing with, I hear. I mean, I'm also arguing with the borrow checker sometimes, so I get it. The rules of the borrow checker are that it enforces is essentially that every access to a value has to be still to an initialized value. It mustn't violate the terms of a loan, so you can't have some overlapping reference to a mutable loan, for example, or make a mutation while you have a shared reference. And the lifetimes of the loan must be valid for the entire duration that you hold on to the reference. Those are the rules. And the things that are relevant to my research are essentially the ones that pertain to references. So initialization and drop check, the things that are related to figuring out the values are still initialized, aren't that interesting. The real stuff comes in when you get references. So that's what I will be talking about for the rest of the talk. And this is a canonical example of someone doing something they're not supposed to. So in this case, you have a value allocated on the stack, the value 17 stored in the variable x, and you're trying to return it. And that's unsafe to do, because when the function returns, the stack is no longer allocated and the value is gone. This is the intuition for why you can't do this. Sometimes it works anyway, because language is question mark. And what happens under the hood is that every time you have a reference in the borrow check, you would have essentially a new inference variable associated with the lifetime. So even if you don't write it, it will be there under the hood. And we will give it a funny name like _1, for example. Great names, very easy to keep apart. And then in this case, this will become a subtyping that happens. So essentially you say that what you're returning is a subtype of what you declared as the possible return value. And you will notice that I put in a mathematical quantifier. This is, so they do this to us academics. They just torture us until we think in terms like this. But this essentially means is that I must be able to plug in any value for A in this expression, and it must still hold. So it's now talking about general stuff. And this essentially boils down to what we call that B outlets A, which we also write like that. It's very confusing when you have the quantifier because now there's 2 colons, but this is what you get. And the intuition for this is that something on this stack frame must live for at least as long as A for any A. And as I said, this is not true, because we can slip in anything, including static, which is anything outside of the function. So this is false, and we've now disproven the statement, because we found an example to the equation where it doesn't hold. And that's when you get an error. So if you change it so that you're returning whatever you put in, the equation instead becomes like this. So you would have essentially A equals A, and now it's fine. But what does the lifetime mean? What goes into the lifetime? So this is another Shakespeare reference. We're stuck with the Shakespeare references because Nico Matsakis named this version of the bar checker Polonius. So I'm going to have to keep doing these kinds of jokes. But what goes into them? Yeah, so we treat them like a set. And this is the intuition that John was trying to give you the other morning. I'm going to completely undermine this in a bit, so I'm very sorry to John. So this is what a Rust program looks like to the bar checker. This is a mirror. This is actually the output from a visualization version of this, which is why it's so long and sort of has these extra edges. But this is what your program becomes. It has a simplified control flow. And what happens is that you, essentially, it means like bits and pieces of these boxes in the graph, essentially. So this one, it can be, is live there, and also there too. So now the crucial question becomes, what goes into the set? And this has changed over time. This is an earlier version of the bar checker that was in the 2015 edition. This is before my time, so this is essentially ancient history. And in this case, we again get this hidden lifetime that's inferred and used for references. And essentially, what the bar checker then did was look for the closest bracket and just like put everything inside of there into the lifetime. And this was annoying because in this case, you would have to, if you wanted to temporarily borrow something and do something with it and then hold on to it for later, you would have to put in these brackets to convince the compiler that really, no, I mean it, this is fine. So that it's like very simple looking for the close bracket would work. This was annoying, so that's why the team worked on non-lexical lifetimes. And what non-lexical lifetimes does is it essentially splits up the program into these basic blocks that you saw before. And then it uses liveness to figure out. So the standard compiler concept of liveness, essentially, will this variable be used at any point in the future? And if it's not used, then it really becomes the tree falling in the woods argument, where if nobody can see this thing through a reference, then it's fine. So the steps that the bar checker is performing is essentially step 1, give each intermediate variable its own lifetime and relate them through these subtyping expressions. So usually values move through these temporary variables until they reach wherever they're going, and that gives you a chain of things. So this looks a bit like that. And then propagate whatever's in the rightmost thing, the bottom thing, backwards across the arrows. Assuming that the value is live. So now everything that's in right will end up in left. From now on, I'm only going to draw these arrows in the direction that they're not propagating. And this is confusing for everyone. So essentially, if these basic blocks are where this thing is live, then it will move on to the second one. And that's how you end up with the final values, and then you check if those are valid. But there's a bunch of edge cases that non-lexical lifetimes cannot handle, and usually they're related to more advanced control flow. So in this case, you have a loop where you're returning early from the loop, and we have to put in a bunch of temporaries because that's how the intermediate representation works. So this is the closest approximation I can give you without completely filling the screen with meaningless code. And this will look something like this. And the intuition for why this doesn't work is roughly that you have, you're mutably borrowing the variable at the top, so you need to have the single reference, but you have two outgoing edges. So it leaks out either through event or it goes back again in the loop. And since everything is live here, non-lexical lifetimes is not able to help you here because it sees that the value is, both of these references that you create can be used at some point. It can either be returned or it can be overwritten. So then you get this error, essentially. So that's one of the reasons we're working on Polonius. So Polonius does two things. One of them is change in perspective. This is the part that undermines John's talk. And the other part is an increase in resolution, what it can reason about. So the change in perspective is that we change it so that lifetimes, which should no longer be called lifetimes, I guess we should call them regions or something, are now a set of loads, a set of things that could be in there, essentially what the reference could refer to. And the second thing is to increase the resolution so that the graph that we construct from these outlets relationships that we get from the subtypings is now dynamic and can change. And I will illustrate what that means. So in this case, we figure out that we have these types of relationships, and in this case, the graph will look something like this, where the buffer flows, or the value from buffer flows both into the temporary and to the events, and everything is live, and therefore you have the problem. With Polonius, we can figure out that these are not usable, both of them at the same time. So we can create two different versions of the outlets graph, depending on which branch you're taking, and figure out that either it's going into temp or it's going into event and being returned from the function. And that's really the difference that gives you. I mean, it's both the difficult thing to do and the thing that gives you extra power. Let's solve this case. So now you can sort of think about lifetimes as a set of something that you put in there. So yeah, you can refer to these variables, and you can also change them depending on liveness. So this gives us this nice for field. That this is another thing that they torture us to do in school until we do, where we have, if everything is static, you get the 2015 bar check. You compute a sense of things without following flow anywhere. If you add liveness to when you propagate values between the nodes in the graph, you get non-lexical lifetimes. And if you also make the graph itself change with liveness, you get Polonius. And there's a useless fourth case that I don't think anyone will want, that I don't even know what it would be able to do, but it would suck. So Polonius began during the work on non-lexical lifetimes as sort of the thing that was left on the cutting room floor to make the deadline. And it was first published in this series of blog posts by Nico Matsakis. And then I worked on extending it a bit for my master's thesis, which is available, and you can read it if you're interested. It has a bunch of nice heat maps that show where various inputs come from. Otherwise, I wouldn't say it's very interesting. It's a master's thesis that is not usually interesting. We promised previously to deliver in time for the 2024 edition. That is absolutely not going to happen, and this is why this was temporarily referred to as the Polonius Apology Tour talk. It's actually a tour because I will also give this talk at a different continent. But no, it's not going to happen. We actually don't have a finished date right now. There's been multiple reasons for that, but it's partially funding and partially other reasons. It's just difficult. What the current version of Polonius that you can get with the the -z option that turns on Polonius it looked like this. And what you're looking at is Datalog. Datalog is a very nice language that can precisely express the set of polytype stuff. So you can, anything that can run in polynomial time, you can write, and you can't write the other stuff, which is cool. And it looks like this. This essentially means that you define an error to be the intersection of invalidated loans at a certain point of the program, joined to, you can think of this as a database join, essentially, joined to the live loans at that point. So it looks a bit like a database join, and it's still a bunch of sets that you copy values between until you reach fixed point. And here's another rule you might want to look at, which describes how. And those terminate in a bunch of ground facts that you put into the system, and then it kind of runs and spits something out. And this is what you get if you run -z Polonius. You've run a version of it that does this. It has a bunch of bugs, but it's like, for some cases it works. But of course, like, because we're working in Rust, we have Datalog at home approach, and the at home in this case is Frank McSherry's very cool Datafrog thing. So we actually write these rules in something that looks like a bit like the thing to the right, where it's actually Rust code that we have done some minimal mangling of the previous version to get. And of course, it's just a bunch of vecs with small values that you move around. We've essentially determined not to go forwards with this. And the reason we've done that is that every part of this was expensive. It's expensive to collect the initial facts. Those can take up a lot of space. We have to do this in a set of separate processes, and it's very difficult to sort of union the things that the Rust compiler already knows with the things that the Datalog engine needs to infer, because it's not adapted to this. And we have a bunch of cheating things, like there are edges from static to anything, for example, that Datalog obviously doesn't know about. And just storing the intermediate results that you would need to get to an error is actually also sometimes taking up a lot of RAM. So that's why. So the plan to get to Polonius is essentially to do this one piece at a time. That's how you usually eat an elephant. You like take little pieces of it until there's no elephant left. So the first step is, among other things, to start to flip the perspective. Don't add the extra power, just flip the perspective and see where that gets us. That's done-ish. We're also working on moving a bunch of higher kinded concerns out of bar check, so that bar check only deals with nice, pristine graphs of outlives relations. I will explain to you after this what that means. But that's done-ish. It's done modulo some optimizations. It's currently costing a bunch of percents in performance that we need to get around. And we're currently working on verifying that if you flip the perspective and essentially take the data structures that store places and flip them in the other direction, that this is actually computing the same output as the regular non-lexical lifetimes bar checker, because we haven't told it to do anything extra. And of course, there are a bunch of edge cases that need tweaking when you do that. That's being worked on. And after that, this will probably become the default. So we will just quietly change the bar check to run half of Polonius. And no one will be the wiser, because this is just an internal concern that you don't have to care about. You might get better errors, I think maybe, ideally, but we're not promising anything. And then there's a separate track, which is essentially just modeling it and figuring out how it works in a theoretical context. I don't know who's working on that. I hope someone. And then the second step is to actually do the increase in reasoning power and start allowing us to create copies of the outlives graph that changes. And this is, of course, the really difficult part. And that's also being worked on. So there's an early version that I think some of that might be available. No, it's just a separate project. I think of it. But of course, like all of these arrows are where the difficulty really is. Because in order to cross that arrow, it needs to be not have bugs, and it needs to be reasonably performant. And that's the part that's difficult, especially being performant is very difficult because we're increasing the reasoning power and we're potentially increasing the size of the problem we're solving by a lot. And the way we think, yeah, I'll get to why I think this will work. So what I've been working on the most recently is to remove concerns about higher candidate types out of borrow check. So originally this was intended to be solved by the new trait solver, but this hasn't been integrated yet, or I don't really know what the status is for that. So we have a temporary solution, which is just essentially, I see Michael smiling, hi. Yeah, which is this. So essentially, when you have this kind of situation where you have a bunch of trait bounds that demand that some variable can be used for anything, you get the same type of situation as when you're trying to return something from the stack, which is essentially that if you have something outliving something that's currently being defined, you don't know what that is, and that, therefore it has to be anything, and therefore it has to be static. And the way this has been handled so far is that the definition order is essentially associated with the universe of a region. So we give every region a number in case it's being in one of these, essentially in brackets in something, in a trait. And then if you find that something is leaking out into something that's in a future defined thing, you essentially just move static into it while you're solving. And that, in this case, this becomes a concern of the borrow checker, because while it's doing the regular logic of moving values through the graph, it now also has to figure out the universes of those things and then move those as well, and so on. And that's tedious and annoying. So the way we went about doing this is that we do a pre-pass through the graph where we figure out if this happens, and we slip in a bunch of extra edges that point to static. And now it's just regular. You take everything that this points to, the arrow points to, and just move everything backwards across the arrow, and you don't have to have any special logic for anything, except for the annoying few special cases where you still need that. But the plan to getting there is that we don't think, we know that we don't usually need the extra reasoning power, and that's why we think this can work. Because you can amortize the cost of running in the more expensive calculation by the fact that you don't need to run it that often. So if we can make a kind of tiered borrow check that first does something very simple, and if the very simple thing passes, then you don't need to go deeper. And assuming we already have this mechanism, we can do that for other kinds of borrow check as well. So that's the plan. My most immediate plan is landing the pull request that does the moving stuff out to the higher kind of concerns, or moving the higher kind of concerns out. But there are also a bunch of things that can happen in the far future, which is why I have this unicorns and rainbows situation here. I had to call in a proper artist to draw the unicorn because I can't draw. And the cool thing that this the cool things are mainly brought by the change in perspective. You can do lending iterators better with the other stuff, and there are a few edge cases that you might care about, but the really cool stuff comes with the change in perspective that allows you now to potentially have a syntax to describe what goes into a loan. So now you can talk about, given that we now have a model that actually is about what is in the loan, that is something that the programmer can see. So these are variables that you have access to, or fields or structs or things. You can have this kind of thing where you say that I'm guaranteed to always return this thing I got in, and not just return the, I mean, this would be meaningless, but you can do things like this. And more importantly, you can do this. So you can say things like, this is a struct that contains a pointer to something that has to be inside of this struct. It's not just something that will be valid for the same amount of time or being accessed for the same amount of points. It's literally the same thing. And that would allow us to have some kind of stricter checks that would potentially be able to relax things like cyclical data structures, which is, of course, the holy grail. That's where we want to go, if possible. And that's pretty cool. You can read more about that in a separate Nico Mentakis blog post that he's also written. And that's all. Thanks for listening.